In this lesson, we'll talk about big idea number 2. How do equilibrium behave if conditions are changed? And how can they be manipulated? And we'll talk about learning target number 4. By the end of the lesson, you should be able to quantitatively determine if a system is at equilibrium by calculating a QC, or a reaction quotient. And if not, describe what will happen in order to get to equilibrium. You'll also be able to describe how to shift an equilibrium in a particular direction using Le Chatelier's principle. Qualitatively, your system has reached equilibrium when you observe no macroscopic changes. Quantitatively, you can determine if your system has reached equilibrium by experimentally measuring the concentration of one of your chemicals and calculating the current ratio of products to reactants, called a reaction quotient, or Q. These are calculated exactly the same as Ks, but using concentrations that you know may not be at equilibrium. You can tell if your system is at equilibrium by comparing the ratio that you have now, Q, with the accepted equilibrium constant ratio, K. Here is how you interpret. If Q is equal to K, it means that your system has the exact same ratio of reactants and products as it should. So your system is already at equilibrium, and the forward and the reverse reactions are the same speed. If Q is calculated to be larger than the accepted K value, the system has extra products. The reverse reaction will need to go in order to reach equilibrium. And if your Q is less than K, it means that your system has excess reactants. The forward reaction will need to go in order to reach equilibrium. Remember, we calculate Qs just like Ks. We take the concentration of the products raised to their coefficients in the balanced chemical equation divided by the concentration of reactants raised to their coefficients. Here is an example. I'm given the following equilibrium equation. At 37 degrees, the equilibrium constant for this reaction is 0.75. That's the accepted value. A container at 37 degrees has the following concentrations present. And the question is this system at equilibrium? And if not, which direction will it have to move? Because I know that these concentrations may not be at equilibrium, I calculate a QC. I'm going to take the concentrations of the products raised to their coefficients divided by the concentrations of the reactants raised to their coefficients. My Q equals 3.25. Since my QC is larger in value than my K, then the system is not at equilibrium. They need to be equal at equilibrium. Because it's larger, it means that I have more products in my system. And the reverse reaction needs to speed up in order to reach equilibrium. Many reactions create equilibria that are unwanted, so how can we change that? Changing environmental conditions, such as temperature, will cause the system to unbalance. It can achieve equilibrium again, but the system will have different chemical concentrations. Depending on what condition is changed, a different value for the equilibrium constant may result. The direction that the system will shift to reestablish equilibrium can be determined using Le Chatelier's principle. It states that an equilibrium will respond to relieve the effect of any change in the conditions that affect the system. This means that the system will always shift in the direction to undo the stress caused to it. This is very helpful, especially if we want to force a reaction to only go one direction. We can force it to move the direction we want by applying the correct stress to the system. There are 3 strategies we can use to purposefully make equilibrium shift. The first one is known as the common ion effect. Adding one of the chemicals involved in the equilibrium will cause a shift to remove the excess. Removing one of the chemicals causes a shift to replace it. This occurs to return the products and reactants back to their original ratio, which means your system will still have the same equilibrium constant. Strategy number 2 is to change the system's temperature. Adding or removing energy from the system will cause a shift to return it back to its original amount. Because temperature changes the relative favorability of the forward and the reverse reactions, this will change the product and reactant ratio and the value of K. And strategy number 3, changing the pressure of your system. When comparing the reactants versus product side of the equation, if there is an imbalance in the number of gas particles, a shift can be created by changing the pressure. Pressure is a measure of the number of gas particles hitting the container. If pressure is increased, the system will shift to reduce the number of gas particles to relieve the excess pressure. If pressure is decreased, it will move to make more particles to replace the pressure lost. Since all gases are affected by pressure equally, this will not change the product to reactant ratio or the value of K. Pressure changes are often caused by changing the volume of the container. There is an inverse relationship between the pressure and volume of a gas. This is Boyle's law that we learned in grade 11. So if you want to decrease the pressure of your system, you increase the volume, or vice versa. Here's an example of how we can apply Le Chatelier's principle. We're given the following equilibrium equation, and we need to describe what we could do to cause the equilibrium to shift in the left direction. So that would make more SO3 gas. And we need to also explain how each method works. Let's take a look at each of our strategies. The first being the common ion effect. If I want to cause a shift in the left direction, I could add either SO2 or O2. This would cause a shift in the reverse direction to get rid of what I added into the system. Let's look at changing our temperature now. This system, as written, is endothermic because I have energy on the reactant side. If I want to cause a shift to the left, I could remove heat from my system by cooling it. This would cause a shift to the left to replace the energy. This happens because with the energy removed, the forward reaction will slow down because it does not have enough energy to create products. And finally, let's look at applying a pressure change. On the reactant side, we have two SO3s. That's two gas particles. On the right side of the equation, we have two SO2s and an O2. That gives me three gas particles. Now, to help out with pressure changes, I use the strategy of adding a plus pressure on the side that has more gas. Now, this allows me to see more easily what the system will do. If I want to cause a shift in the system to the left, I would cause a pressure increase in my system. That will make the reverse reaction go faster. Whenever you increase your pressure, the direction that produces less gas particles becomes more favored. Here's one misconception that some people get about changing pressure in an equilibrium. Some people will look at this equation here and say, oh, I have pressure on the right side of the equation. That means I need to increase the pressure on the reactant side. Remember, this is an equilibrium, which means the reactants and the products are in the same container. You cannot change the pressure of one of the sides. You have to change the pressure of your whole container. Watch out for that when you're writing your discussions or explanations of pressure changes using Le Chatelier's principle. Have a look at example number 2. Here we have an equilibrium producing ammonia gas. which is a very heavily used industrial chemical. We want to cause this equilibrium to shift to the right to make more ammonia. Describe 3 methods that you could use and explain how they would work. The answers to this example you will find on the next video.